Okay, now we're going to look at another problem. This is another coupled oscillator problem. It's a double pendulum. So here's the first pendulum bob, and here's the second. We're just going to apply F as ma, just like we did last time. So we start by drawing the forces on the first mass. So there's a tension in this first string. Let's just call that T1. Then there's a tension in the second string, that'll be T2, and finally there's the weight of the bob, mg. Okay, now we're going to do F equals ma on this mass, so we should think about the coordinate system. Well, pendulums we typically use the cylindrical coordinates, so we want to know the r hat direction. So r hat will be away from the origin, which is up here, so that's r hat, and then theta hat's in the direction of increasing theta. And so we're going to want to find components of all those forces in the r hat and theta hat direction. And we're mostly going to be interested in the theta hat direction. So there's theta hat right there. So T1 you can see is radial. T2, well, this phi angle, we should note, is all the way to the vertical. So that's phi. So for components of mg, we need this angle here, which is theta. And for components of T2, we need this angle here, which is phi subtract theta. So if we're going to sum the forces then in the angular direction on M1, well, there is going to be this mg component in the negative theta direction. So I should use a subscript. This is m1g sine theta. That's in the negative theta direction. And then we've got a T2 sine component in the positive theta hat direction. Now, in the radial direction, sort of along the string, we're going to assume the angles are very small with fairly low speeds, and therefore the chord tensions are approximately just going to end up equaling the weights. So the tension in this second chord is just going to equal the weight of the lower bob. So T2 will be approximately m2g. And then the first tension in the first string is just going to be approximately both weights, since it's supporting both pendulum bobs. So we proceed with our analysis. Now, we had for our angular direction sine terms, but for very small angles, we'll just take the first term in the Taylor series. So sine theta will be approximately theta, and sine of phi minus theta will be approximately phi subtract theta. So we substitute that in then to the force equations. And so we have, for the sum of the theta forces, so minus m1g, so sine theta we replace with theta, and then it was substituting in for the tension force. We say it's about equal to m2g, and then we had sine phi minus theta, so we're going to say that's approximately phi minus theta, and that equals the mass times the theta acceleration. Now, remembering our kinematics, we know that a theta is r theta double dot plus 2 r dot theta dot, and r is just the length of the pendulum, which is of course a constant. So that means that L dot is 0, and the only term we have is L theta double dot. So we substitute that in. On the, I'll start with the right-hand side here, so it'll be ml theta double dot, and then I've got this stuff on the other side. And you can kind of see here already some terms that look a lot like our analysis from yesterday with the 2 masses and 3 springs. So we're just going to solve this for theta double dot. And so we're just dividing through by m and l. Now I should emphasize this is m1l, right? I've got to be careful. And also up here, I'll do it in red for emphasis. This were the forces on m1, so that's m1a. Alrighty, because I have both m1 and m2 terms in here. Alright, so just dividing through by m1, I get minus g over l. And then I've got 2 theta terms, so I'm going to gather the like terms. So there's going to be m1 plus m2, and then I divided by m1, and those are the theta terms. Then for the phi terms, I'm dividing through by m1, so I just get that expression right there. And you can see that we're getting ready to load this into a matrix. Let's continue with the force analysis now and consider the forces acting on m2. So now we consider the forces on m2. So we're going to have, of course, the tension here, tension 2, and then the weight of the mass, m2g. Now, for our origin being here on m1, we're going to be looking at the phi hat direction, which is this direction right here. Now, because mass m1 is actually accelerating, right? It's accelerating in this direction here, and we just showed above, doing our kinematics, that the acceleration of m1 was L theta double dot. And that acceleration, I mean, theta hat would be in this direction. So this is actually in the negative theta hat direction. That's just because theta is decreasing and theta double dot is actually negative. All right, so the point is that the mass is accelerating, and that means, because it's accelerating, if we use that for our reference frame, then we will observe within that reference frame a fictitious force. And the fictitious force will be opposite to the direction that the reference frame is accelerating. So the reference frame acceleration is this way. That's the way m1 is accelerating. So there will be a fictitious force opposite to that. And this fictitious force is really just an inertial effect. So let's just drop that force in there. There it is right there. So that is the fictitious force that acts on m2. Now the magnitude of that fictitious force is ma. So this is m2. Oops. Just lock that in place. There we go. So this is, with the pen tool again, sorry about that, m2. And then it's going to be L theta double dot, because that's the acceleration. But because theta double dot is negative, and we want this force to have just a positive magnitude, we put a minus in there. So that's the magnitude of the fictitious force. That's a positive number. Let me just try drawing that a bit more clearly. This is going to be theta double dot. Alrighty. So if we sum the forces then on m2, and we're going to be looking at forces in the phi direction. Now, if that angle's phi, then this angle is also phi. So we see that it's m2g sine phi in the phi hat direction. And then this angle right here, this will be phi minus theta. It's right here. Phi, subtract theta. And so there'll be like a cosine phi minus theta for the phi hat component of the fictitious force. So, summing the forces then in the phi direction, we get minus m2g sine phi, and then minus m2 L theta double dot cosine phi minus theta, and that's got to equal the mass times the acceleration in the phi direction. Now, using the small angle approximation, of course, this is just going to be m2g sine of phi is approximately phi. And then, in the small angle approximation, cosine is approximately 1. So that means this term here is just 1, that cosine term. And we'll again do kinematics, and assuming the pendulum cord is the same length, then this is going to be L times phi double dot. So this is the net force equation for M2. And so now we're just going to put those two equations together, the net force on M1 and the net force on M2. That's on the next slide. So here we have the net force on M1, and here's the net force on M2. Now, to set this up in matrix form, you notice that here there's actually theta double dot. So we're going to have to solve the first equation for theta double dot and then substitute it in here. Now, we had previously done that, and for just multiplying the L over, because I need an L here, L theta double dot, we could substitute in this expression here in terms of theta and phi. All right, so we sub in for L theta double dot, and then we gather the terms in phi and theta. So, pulling out a minus sign, for the phi term, we're going to have m2g times phi, and then we're going to have from m2 times this guy, we're going to have m2 squared over m1 times g, and that'll be the phi term. And then the theta term is just what we had right here. Now, because we're subtracting, it ends up being a positive. We're subtracting L theta double dot. And we're multiplying, of course, by m2. And so there we have it finally, the equations, the force equations for the two masses on a coupled pendulum. And now you can see that we've got theta double dot in terms of theta and phi, and we've got phi double dot in terms of theta and phi. So these equations are written down for you on the next slide. And so we just divided, we pulled out the g, divided by L, and so here's the theta double dot equation. So just, matrix multiplication, so it would be this term multiplied by theta minus this term multiplied by phi, and then all of it multiplied by g over L. And then the phi double dot term, you would take, this times theta, this is just the rule for matrix multiplication, and this guy by the phi. All right, so now if we look at this equation, we see again we've got symmetry on the main diagonal, and then two different off-diagonal terms. We had previously shown that a 2 by 2 matrix of this form has these two eigenvectors and these two corresponding eigenvalues. So once we've got the differential equation in the form of this matrix, we have the answer. We know that theta and phi are going to have these two normal modes. So the first normal mode, well, theta and phi are proportional to each other and both positive. So they're both sort of swinging in phase, with phi having a much larger amplitude. And that one, so that's one of the normal modes. The other normal mode, they're opposites of each other. So this is sort of like an antisymmetric vibration. Again, the amplitude for phi is bigger than 1, so the lower mass has a bigger angular amplitude than the top one does. But it's similar to the coupled spring oscillators, because here we've got, a symmetric normal mode and an antisymmetric one. And that ugly expression there is the expression for the eigenvalues. So what we've seen here is that when we wrote F equals ma for this coupled pendulum and put it in matrix form, we again get two normal modes, and these normal modes have physical significance, and we'll try and demonstrate these normal modes to you when we meet together in class.